My dad is going to solve this problem for you. I hope you find it helpful. Now I'm going to read the first sentence. A 1.5 kg mass is hooked onto a relaxed spring. K equals 50 N dash M and released from rest.
All right, Lily, I'll take it from here.
Okay, bye.
Thanks, Lily. All right, so we have a 1.5 kilogram mass hanging from this spring. So first, let's set up a new diagram. So here's how I would look at this. So the spring is here, and there's no mass attached to it yet. So we know that the spring constant is 50 Newton per meter, and then we attach this 1.5 kilogram mass to the spring. Now, if we release this from rest, the mass is going to start up here, and it's going to go all the way down until the spring brings it to rest. The first question is, how far will the mass fall before the spring brings it momentarily to rest? The easiest way to do this is using conservation of energy. So at this point up here, we're going to say that the mass has potential of gravity. And whenever you use potential of gravity, so that's mgh, h is measured from the 0 point. So for this situation, we're going to put the 0 point at the lowest point in the problem, which is all the way down here. So we're going to say that this is our h equals 0. There's no other energies up here. At the highest point where the mass starts, there is no potential of spring. The reason for that is that this spring is fully relaxed. It's not stretched and it's not compressed. And there's no kinetic energy, but kinetic is also 0 because the mass has no velocity. So the only energy we start with at the top is potential of gravity. So the mass falls, it comes down, down, down. At the lowest point, it's going to stop momentarily. So if we look at the three energies again, so potential of gravity, potential of spring, and kinetic, well again, kinetic is going to be 0 because the mass momentarily stops. The spring brings it to rest. And potential of gravity is also going to be 0 because earlier we said that down here this was our 0 point for potential of gravity. Now, potential of spring, the equation for that is 1/2 kx squared. But if you think about it, the distance that the spring was stretched in this equation for potential energy of spring, x is how far the spring is stretched or compressed, and that distance is h. It's the same as this. It's the same variable, so we'll just call this 1/2 kh squared. So to solve part A, it's really just conservation of energy. There is no loss of energy due to any sort of friction that was mentioned. So basically we can say mechanical energy initial equals mechanical energy final. And of course by mechanical energy is these three right here. So our initial was up here. The only mechanical energy that we start with, the only initial mechanical is potential of gravity. And then the final mechanical, the only final mechanical energy we have is potential of spring. So this is going to be mgh equals 1/2 kh squared. One of the h's cancels, and we get h equals 2mg over k. So plugging in our values, 2 times 1.5 kilograms, gravity is 10, and K is 50 Newton per meter. This comes out as 0.6 meters, which is the answer to the first question. Okay, second question. So what is the amplitude of the resulting oscillation. So let's just reset this. I'm going to clean this up. So again, we have our spring right here. Mass goes on it. And what we figured out was that it drops 0.6 meters. Yes, Lily?
I need a calculator.
You know what? I need this calculator.
Okay, do you have another one? Can I use your phone?
Use my phone. Okay. Okay, so 0.6 meters is how far it falls total. So the answer is going to turn out to be, so what amplitude is, the definition of amplitude is defined, there's a definition for amplitude. It's the maximum distance from the equilibrium position. And the equilibrium position, if this oscillation dies, it's going to die to the middle. And that's where the equilibrium position is. The equilibrium is right here in the middle. So let's label this as the equilibrium position. So the answer is going to be, you take this 0.6, divide it in half, there's going to be 0.3 meters maximum distance off equilibrium up here, and then there's going to be 0.3 meters off the equilibrium down here, and that's the answer. But I'll show you another way to calculate this. So equilibrium position, if you remember back to earlier in the semester, the definition of equilibrium is when your acceleration is 0, or in other words, the net force is 0, right? Because F net equals ma, and if your acceleration is 0, that means that your net force is going to be 0. So why is this significant? Well, let's look at the mass when it's at the equilibrium position. So it's in motion here. This mass is moving, but as it passes through the equilibrium position, for a split second, right as it passes through here, the acceleration is 0. Now that doesn't mean the velocity is 0. In fact, at the equilibrium, velocity is a maximum. Velocity is a max right there. So why is acceleration 0? Because as it passes this midpoint, the two forces on the mass are gravity down, we have mg down, and then the upward force is force of spring. Because if you think about this, as the mass pulls the spring down, the spring exerts a force back. As soon as this spring starts getting pulled downward, it exerts an upward force. And you should note, this force of spring is not constant. It changes as the mass moves. So for example, when the mass is down here, it's going to be a much greater force of spring because the spring has been stretched farther. But right here at this midpoint, this force and this force are perfectly equal, which is why we call it the equilibrium. The net force is 0. So to show a calculation for part B, we can just sum the forces at the equilibrium point. We have force of spring up, so our sign convention is up is plus, down is minus. Force of spring up minus mg down. Sum of the forces equals ma. Our a is 0, because that's the definition of equilibrium. So we have force of spring equals mg. Now, the equation for force of spring is k times x, where x, let's just pretend we don't know the answer yet. X is how far, let's erase this. X is how far the spring was stretched from its starting point. So we have kx, x is how far it stretched, is equal to mg. So x is going to be mg over k, which is 1.5 kilograms times 10 for gravity, divided by k, which is 50, and this comes out as 0.3 meters. 0.3 meters. So we have, so if that's 0.3 meters, then this has to be 0.3 meters, because we already figured out the total distance is 0.6. All right, now question C, how does your answer to part A compare to your answer to part B? So if you look, the answer to A is exactly double the answer to B. And the reason for this is the amplitude on each side of the equilibrium is the same. So if you add up these two amplitudes, it gives the total distance from highest point to lowest point. Okay, question D. Let's revert this. So there's an equation for this. In fact, here, I'll show you on the College Board equation sheet. We'll just take a quick look here. So equation sheets. So on the College Board equation sheet, so you don't have to memorize this equation, but there is an equation for, zoom in right here. So this equation right here that I'm moving the cursor around, so this is the equation for period for mass on a spring, and then this one here is for a pendulum. So these are really important equations when it comes to period. So the way we're going to solve part D is we're first going to solve for period. So the question says frequency, but if we solve for period, and again, what do we mean by period? So the mass goes on the spring and it starts to oscillate down to the low point. The period is the time it takes to go from here down and back. It's one complete cycle is what the period is. And the equation for this is 2 pi square root mass over spring constant. So we're calculating the period. Mass is 1.5 kilograms. This is 50 newtons per meter. So the period works out to be 1.08828 seconds. Now, there's a relationship between period and frequency. The relationship is this. They're the inverse of each other. So if we know the period, the way we find the frequency is by taking the inverse of the period. The example I always give for this is imagine I clap my hands twice per second. So something like that. So if I clap my hands twice per second, the frequency would be 2 hertz, which literally means 2 times per second. Per second is what hertz means. Hertz is per second. So if I clap my hands 2 times per second, what would be the time for one hand clap, which would be the period? Period is 1 over frequency. So that would be 1 over 2 per second, which would be equal to 0.5 seconds. If I clap my hands twice per second, the period of one clap is going to be half a second. Period and frequency are the inverse. So if we know the period of this oscillation, the frequency will be the inverse, which comes out to be 0.92 hertz. Okay, part E I think is the trickiest part. E is the trickiest. So this is going to be conservation of energy. So let's set this up again. So here is our mass. It's going to start up here and it's going to drop down to the lowest point. And we want to find the velocity at the equilibrium position. So the equilibrium position is in the middle, right here, and we already know these distances. This is 0.3 meters here, and then this distance here is 0.3 meters. I'm going to make our starting point, so we're going to say mechanical energy initial, so we'll say like at position 1 equals mechanical energy at position 2. I'm going to say that position 1 is here. This will be our initial, and then the equilibrium position is right here. This will be our position 2, right there. So we have initial and final. So let's go through our energies. Initial, we have kinetic, we have potential of gravity, and we have potential of spring. So at this point right here, the mass is not moving. At the lowest point, it is stopped. So the kinetic is 0. We can ignore kinetic. Potential of gravity, it all depends upon where we put our 0 point. To me, it's pretty obvious that we want the 0 point to be here, right? We're going to say that this is our 0 point. So therefore, there is no potential of gravity there. And potential of spring, do we have potential of spring? Absolutely, because the spring started up here and the spring got stretched to get down to this point. So I'm going to call this distance x1. The distance that the spring got stretched from up here to the lowest point is x1, and that is 0.6 meters. So mechanical energy 1, this simplifies down to potential of spring, which is going to be equal to 1/2 kx1 squared. Okay, now let's go to position 2. Let's list our energies. At position 2, kinetic, potential of gravity, potential of spring. So do we have kinetic energy at position 2? Absolutely, because the mass is moving, so don't cross that out. So at position 2, we will have kinetic. What else will we have? Will we have potential of gravity at position 2? Well, did we rise? So we set our 0 point to be down here. Did we rise above our 0 point? Yes, we did. So don't cross out potential of gravity. So we're going to have potential of gravity, and let's just talk about what that's going to be. That's going to be mgh, where this h is going to be 0.3 because that's how high we came off the 0 point. All right, and then third energy, potential of spring. Do we have potential of spring at the equilibrium at position 2? Yes, we do, because remember, the spring started up here. Basically, our 0 point for the spring was up here. This is our 0 point when it comes to the spring. When we start stretching the spring is going to have energy. So we're going to have plus potential of spring. The equation for that is 1/2 kx squared. I'm going to call this x2. And x2 is going to be how far the spring was stretched from up here. Right? The spring started here, it got stretched to here to get to position 2, so we'll call that x2, that's squared. And x2 is going to be 0.3. So let's plug everything in. So now we're just working with this equation right here. So this is going to be 1/2 mv squared. This is going to be mgh, where we said that h is 0.3. And then this is going to be 1/2 kx2 squared, like that, where we said x2 is also going to be 0.3. So plugging numbers in, this will be 1/2. I'm going to leave units out here. K, well, let's put it in, newtons per meter. X1 was 0.6, right? That's 0.6. That's how far the spring was stretched to get to the lowest point. Squared equals 1/2. The mass is 1.5. Velocity is what we're looking for. Mass is 1.5. G is 10. H is 0.3. And then last part, this part right here, 1/2 K Newton per meter. X squared, the x there is 0.3. Don't forget to square that. And then now, the only thing missing is velocity. So if you solve this algebra out, velocity comes out as 1.73 meter per second. You're just solving for v. Right there. Okay, last question. Plot a position versus time graph for the mass's motion. So let's revert this, do it one more time. So our mass spring starts right here. Now, we're going to create a position, which is measured in meters, versus time graph, measured in seconds. And it says here, let the equilibrium be the 0. So the equilibrium is right in the middle. This is going to be our 0 meter position, and then this is going to be some positive, let's call this positive y, and then this will be negative y. So on our position time graph up here, this would be our positive y position. This would be our negative y position. All right, now the mass starts up here. So we want the graph to start up here. This is where the mass starts. And the mass is released. Now, this really goes back to the very, very start of the year. If you think about a position time graph, so I'm just going to draw another one here. So position time graph, one of the important things here is that the slope of a position time graph, so slope is rise over run, the rise is meter, the run is second, so the slope is meter per second, which is velocity. So how does that relate here? Well, if you think about this, when the mass is released, what is the starting velocity of the mass? So when the mass is very first released, the velocity is 0. So the slope of our position time graph should start out 0, right here when it starts, 0 slope. Now, where is the mass traveling fastest? Where is the velocity greatest? Well, that's going to be at the equilibrium position. So it kind of goes like this. The equilibrium position, so this is the equilibrium position. Velocity is a max right here, and then at the amplitudes, velocity goes to 0. So this will help us graph this out. So as the mass passes the equilibrium, the velocity is maximum, which means the slope should be maximum. So it's going to go 0 slope to a maximum slope as it crosses the equilibrium. So the equilibrium is right here, right? When the position is 0, that's the equilibrium. So this is equilibrium. Slope is a maximum. Now, when it gets to the other amplitude down here, the slope has to go to 0 again. So the graph is going to go boom. When it reaches this other amplitude, the slope goes to 0. Now the mass starts heading back up again, right? It changes direction. The velocity becomes positive because it's moving up, so the slope becomes positive. The slope should become a maximum as it crosses the equilibrium. The slope should be a maximum. And then when it reaches the amplitude up here again, the slope should be 0. So it's going to be a graph that kind of looks like this, 0 slope at the amplitude for 0 velocity, and then as the mass crosses the equilibrium, the slope should be a maximum, like this. Okay.